from current slide. And the announcements, I think you've heard most of them. I don't know if the business office is open again. They sent us this email that until further notice, do not add or subtract courses for student award or process grant aid, complete registration until further notice. They haven't notified us, but I assume it should be done soon if it hasn't been done already. If you know of anyone in a second mini-term and a first mini-term course, the deadline to withdraw is tomorrow, and the final exams are late next week. And second mini-term classes start the following Monday, which is the 14th. Volleyball team. Today's what, the 3rd. We'll be playing tomorrow. Coastal Alabama, but unfortunately that's down in Bruton, Alabama, wherever that is. I don't know for sure, but it's somewhere down there at 2 o'clock at 2 o'clock in the afternoon. Then on the 9th, which is next Wednesday, so we'll have 28 times to make that much later. Well, if you're graduating, there's a meeting today at 1 on this campus and 5:30 on the other campus. I think anyone who's hearing this probably won't hear this until after that. So there is a scholarship summit coming up next week. I think it's Tuesday and Wednesday of next week. And all these schools, I read to them to you. Of course, I won't go through them again. If you want more information, it's here. And the NASA's Community College Aerospace Scholars Program accepting applications through October the 16th, which is less than 2 weeks away. So if you are interested, move on that soon. All the information that I have, you can get off that sheet. You're welcome to it. Okay, any questions on anything we've done so far? Okay. Now, I believe where we got to last time was how to go about determining the inverse of a matrix. Okay? And we had a pretty simple 2x2, and we came up with an inverse, and then we're going to do this a slightly different way and see if we get the same results. The other way was pretty long and a lot involved with it. Here's the better way, and especially on a 2x2, it's just about the same, okay? But anything bigger than a 2x2, this is the way to go, the way I'm about to show you. Otherwise, you'll be solving equations forever, it seems like. So here's what you do. The one that we're trying to find the inverse was 1, 4, -1, -3. Okay? Adjoin to that the identity matrix, 1, 0, 0, 1. Okay? And then row reduce the this new matrix you have. What do you want when you row reduce? In upper left, you want a 1. We've got it. Okay. What you want after that? 0 under it. And how do you get that? Row 1 plus row 2 is the new row 2. Okay, so do that, and that becomes, you leave the first row alone, 1, 4, 0, or I can't write, 1, 4, 1, 0. But the second row becomes what? 0, 1, 1, 1. Okay, you got stuck on 1s, didn't you? Okay, what do you want next? First non-zero entry in row 2 to be a 1. Hey, we got it. What do you want after that? 0 above it. How do we make that happen? Yeah, -4 times row 2, add it to row 1. And that's the new row 1. Okay, so this time we're using row 2, so write it down, 0, 1, 1, 1. That better be what we had before, yep. And then do what it tells you. Minus 4 times row 2, add to row 1. What you get? 1, 0, negative what? 3, and negative 4. Okay? If all was right with the world, that should be a inverse, or whatever you called that first function. That should be the inverse of this one. Okay? Now, and sure enough, that's what they got in the book, so I'm hoping we were right. Yeah, they called this one A. You adjoin that with the identity matrix. Do the process, you wind up with the identity matrix and A inverse adjoined to that. Now, if you ever get to the point where you can't get a identity matrix here, that means that's not invertible. That was a singular matrix. You can't convert it anyway. So you won't get an answer then. But if you do this and you do get an identity matrix, then you get the one and only inverse matrix for this one. Okay. Now, that procedure or algorithm, whatever you want to call it, works for any size matrix, n by n. If A cannot be row reduced, that's what I was just saying, to I sub n, then A is non-invertible or singular. That procedure will be formally justified in the next section after introducing the concept of elementary matrices. For now, here's a summary of that algorithm. So it's basically what we just did. Here's a summary of it. Okay. By Gauss-Jordan elimination. Number 1, A has to be square. N by n. Has to be, otherwise there's no way you'll have an inverse matrix to it. Okay? Now, so the first step is take A, adjoin it with the identity matrix. So this produces a n by 2n matrix. Okay? Because you still have n rows, now you have twice as many columns. And by the way, this is I sub n. That means it's n by n also. Okay? So that gives you A on the left and I on the right. Okay? That's called adjoining I to A. So that process is adjoining I sub n to A. A then right at it. You don't put a line through it. I just wrote it to make it easier, hopefully to see. Okay, that's the first step. Number 2, now you do your row reducing. And if possible, if you can't do it, there is no inverse. But if you can do it, row reduce. Okay, and it's not let's see. It's not just getting it to row echelon form, it's reduced row echelon form. That's why they use the term row reduce. Okay? Now, if when you row reduce it, you do come up with I on the left, which if it row reduced properly and would do it, that's what you're going to wind up with because it was a square matrix. That'll be an I sub n again. But then what is, you'll find the join to that is what we call A inverse. Okay. Now, if that doesn't come up to be an I sub n, then you're not going, you'll know that A was originally not invertible. All right. And then the last step is check your work. It's okay. Okay. Check your work. Well, how do you check this? Well, you multiply A, 1, 4, negative 1, negative 3, by its supposed inverse, which is negative 3, negative 4, 1, 1, and see what you get. so let's do that. Is that multipliable? Of course, 2 by 2 by 2 by 2 is going to give you a 2 by 2. First entry, what will it be? 1, perfect. Next entry? Yep, 0. Next entry? 0 again. Perfect. And the last one? You didn't even try, did you? Okay. Yeah. 4 minus 3 is 1. You're absolutely right. Okay. You knew it was going to be a 1, didn't you? All right. So sure enough, you get the I matrix. And if you wanted to, you could reverse the order and multiply them again. But guess what? You're still going to get the I matrix. All right. Now, before you get to example 3, at the bottom of the page, there's another linear algebra applied, and it's talking about Hooke's law, which talks about elasticity of objects, and the formula is there, and they write it in vector form, that the D, which is your deformation, is equal to F, which is a flexibility index. That's not a force, but flexibility index. And W is the force. So I don't know why they use such weird things. I would have said capital F bold would be your force matrix, and let W, whatever you want to be, do the flexibility matrix. But I guess they use L for flexibility. So then if you did an inverse matrix of that flexibility, you would get a stiffness index or stiffness matrix. So there are practical applications for the inverse matrices like that. It seems like in physics and in many of the other sciences, once you do something, you always try to see a way to undo it. And basically, your inverse matrix works to help you do that. All right, so that was an easy 2 by 2. Let's move up to a 3 by 3. Find the inverse of this matrix. Again, they're calling it A. That's their favorite name for a matrix. 1 minus 1, 0. 1, 0 minus 1. And negative 6, 2, 3. Okay, I don't even want to write that last bracket down, because what are we going to do next? To find the inverse? That is a 0 there. It's a pretty ugly 0. How will you go about finding that inverse? Okay, wait, before you do that, the what? Identity matrix? Yeah. And what is that? Got it. Okay. Now we do our row reduction. First thing we want to happen, first non-zero entry in row 1, we want to be a 1. Ding, ding, ding. We've got it. Next, 0 below it, and how do we make that happen? Plus row 2, and that's going to be the new row 2. So let's do that. And that means we're using the first row, so just write it down. 1 minus 1, 0, 1, 0, 0. I said minus 1 and wrote a minus 0, whatever that is. That makes no sense at all. Okay. 1 minus 1, 0, 1, 0, 0. Do what you just said to row 2, and that would be 0, 1, negative 1, negative 1, 1, 0. Perfect. Okay. Now, what do we want next to happen? 0 below that, and that means that negative 6 has to become a 0. How do we make that happen? 6 times row 1 plus row 3 is the new row 3. My 6 didn't draw too well. There it is. So do that, and what do you get? 0, negative 4, 3, 6, 0, 1. Okay, good deal. Okay, what's the next thing we want to happen? Go to the second row. You want the first non-zero entry to be a 1. We've got it. And then what? Zeros above and below it. So let's deal with the upper one first. How do we get that negative 1 to become a 0? Row 2 plus row 1 is the new row 1. All right, so let me come over here, and I'm going to write down row 2 because that's the one we're using. 0, 1, minus 1, minus 1, 1, 0. Boy, that's symmetric, isn't it? In some sense. Okay, do what we said we're going to do to row 1. 1, 0, negative 1, 0, 1, 0. Got it? What's the next thing we want to happen? Okay, and how will we make that happen? 4 times row 2 added to row 3 becomes a new row 3. Okay, do it. 0, 0. Second, negative 1. Perfect. Okay, 2. Second, 4. Is that what you said? Okay, and 1. Got it. What's the next thing you want to happen? First non-zero entry in row 3, we want to be a 1. What is it now? Negative 1. How do we make that happen? Yeah, multiply or divide negative 1 by everything in there, which is simply, if I can get away with this, make that a plus and the other 3 minuses. That works, doesn't it? All right. That's done now. What do we want to happen next? Well, 0 is above that 1. How do we make that happen in row 1? Row 3 plus row 1 becomes the new row 1. So let's come over here and do it. I'm going to write down row 3. 0, 0, 1, negative 2, negative 4, negative 1. All right. And what's the new row 1? 1, 0, 0, negative 2, 2, oh wait, no, negative 2, okay, and negative 1. Is that right? I'm sorry. No, it's a positive 1, isn't it? No, it's a negative 1. Okay. You're trying to confuse me, aren't you? Huh? I catch you. Okay. Well, I can't get my eraser to come up. I had it right, and I erased it. Okay. I believe that's the negative 1, isn't it? Oh. Oh, plus, okay, I'm sorry, negative 3. Okay. I got sort of lost in the sauce there. I was trying to keep up with you and couldn't hear. I can't get my pen to come back. Come on back, pen. Come on. You can do it. There you go. Negative 3. All right, let's make sure. 1, 0, 0, negative 2, negative 3, negative 1. Got it. What's the next thing we want to happen? 0 above that leading 1 down there. And how do we make that happen? Row 3 plus row 2 is the new row 2. Okay? And what would that be then? 0, 1, 0, negative 3, negative 3 again, and negative 1. All right. If all worked right with the world, which I hope it did, we got a really negative matrix here, don't we? Let's see if that's right. Negative 2, negative 3, negative 1, negative 3, negative 3, negative 1, negative 2, negative 4, negative 1. Sure enough, that looks like it works. Let's take that, multiply it by the one here. Okay. Okay, that's a minus sign there. And let's multiply it and see what we get. When we multiply this times that, we will get a 3 by 3. This is just to confirm we did it right. Okay? 1 entry would be a negative 2 plus 4 would be 2. Okay. Negative 2, I'm sorry, plus 3 would be 1 plus 0 is 1. Took me a while. Next one. Yeah, I'm doing it. Sorry. Stand up. Okay. Multiplying A by A inverse. We think this is A inverse. Okay. This is what we're proposing to be A inverse. So we're checking it by multiplying A by A inverse and see what we get. Okay. Do you agree the first one's a 1? Okay. Let's do the next one. You're going across? Okay. So that will be negative 3 plus 3 is 0 plus 0. Oh, sure enough, that's 0. All right. Next one, a negative 1 plus 1 plus 0. That's a 0. Okay. A 2, 1 entry would be a negative 2, 0 plus 2, 0. 2, 2 entry be a negative 3, 0, plus 4. Sure enough, that's 1. 2, 3 entry, second row by third column. Negative 1, 0, plus 1, 0. 3, 1 entry. Woo, big number here. 12 minus 6 minus 6. Sure enough, that adds to 0. Then the next one is 18 minus 6 would be 12, minus 12 would be 0. And finally, 6 minus 2, 6 minus 2 is 4, and minus 3, sure enough, is 1. So that does check. That does give you an identity matrix. You could go back and multiply the other way too. I don't think there's any way in the world that won't give you a identity matrix. So that seems to be what we've got. And they got in the book also exactly that matrix. And you confirm it by multiplying A by A inverse, and you got an identity. And if you want to reconfirm A inverse by A, and you also should get the identity matrix. All right. Any questions? Pretty straightforward, huh? Okay. Now, let's try another one. A is 1, 2, 0. 3, negative 1, 2. Negative 2, 3, negative 2. All right. Oops. Yeah. Oh, man. I am stiff. I don't know why. I think end of the week. I just wear out. Okay. How do we proceed? Identity matrix is 1, 0, 0, 0, 1, 0, and 0, 0, 1. All right. What's the first thing we want to happen? 1 in the upper left. We got it. All right. Good deal. What do we want to happen next? And how do we get that? Negative 3 times row 1 plus row 2 should be the new row 2. Okay? So let's do that. We're going to use row 1, which is 1, 2, 0, 1, 0, 0. And what's our new row 2? 0, negative 7, 2, negative 3, 1, and 0. All right. How about, what's the next thing we want to happen? 2 times row 1 plus row 3 is the new row 3. All right, do it to it. Zero. What'd you get? 7. Perfect. Negative 2. All right. Negative 2, right? Okay. I'm lost now. Okay, 0 and 1. All right. Now, time out. Don't blindly go for it. Let's take a look at something. If you were to add these two rows together, what do you get? 0, 0, 0. And whatever you get here doesn't matter. You're never going to make that an identity matrix, not with 3 zeros at the bottom here. So as soon as you see that, hold the presses. This is a singular matrix. This was a singular matrix. It's not inverted. You cannot invert it, so don't waste the time trying. Okay? It can't be done. They did one more step and got 0, 0, 0, and then whatever they got in the rest of it doesn't matter. As soon as you saw that, then stop. There is no inverse. Now they're going to go back. Okay? Gauss-Jordan is the way to go for big matrices, 3 by 3 and higher. That's the way to go. It's pretty efficient computer-wise. It's just a good way to go. However, for your 2 by 2s, there is an easier way. And we're lazy, right? We like to find the easiest way. And here's what we're going to do. In the next chapter, we're going to introduce a concept called the determinant. Well, we're not going to introduce it. You're introduced to it now, okay? And in a 2 by 2 matrix, a determinant is a very simple thing, okay? It's not too bad in any other, but in a 2 by 2, it's so simple. So let's say we have a matrix A, and we're going to keep it very generic right now. A, B, C, D. Okay? Those represent numbers. Okay? That's a 2 by 2. The determinant of A, and they don't show you the symbol for that. Different books use different ones. I want to make sure I'm going to use the same one the book does. Yeah. They look like absolute value bars. And if they were anything else other than that, they would be absolute value bars. But with a matrix in between, they're not. So the determinant of this matrix and of any 2 by 2 matrix, you do the down diagonal, multiply those two together, that gives you AD, and then minus the product of the up diagonal, minus CB, or BC. It doesn't matter which order you do that multiplication. That's called the determinant of the matrix. Now, here's the catch. If that determinant is 0, then what that implies, we have a non-invertible matrix. Another way to say that, a singular matrix. Okay, I can't write, but you get the general idea. Okay. However, if this thing is anything not equal 0, negative, positive, fraction, decimal, huge number, small number, whatever it is, if it's not 0, then this is invertible. If that's not 0, that implies it is invertible. Meaning non-singular. Okay, non-singular matrix. Any number, if that product, AB, AD minus BC is CB, it doesn't matter which way you do it, is anything other than 0, that has an inverse. All right. Now, that's not just a test. You also use that inverse. So the A inverse, you use the determinant. A inverse is then 1 over the determinant. Okay? And remember, the determinant can't be 0. If there's 0, you can't do this. Okay? But if it's 0, you're not doing it because that's a non-invertible matrix. So if it's not 0, you can write its reciprocal. And then what you write down, this is the fun part, okay? You reverse the main diagonal. Make it DA rather than AD. Next, you negate the other elements. So that would make it a B minus B and a minus C. So basically, that gives you your inverse matrix. Okay? It's 1 over the determinant of that matrix times this manipulation of the matrix. Flip the values on the main diagonals, negate those on the other diagonal. Just negate them. Don't move them, just negate them. Okay. So, let's see if we can do this. I'm going to erase what we've got here. I can't believe that. Oh, that's right. I never took it out of my pocket. Okay. Yuck. Okay. All right. Let's do matrix A. 3, negative 1, negative 2, 2. First question, doesn't have an inverse. How do you check that? Find the determinant. What is the determinant of A? Second. Okay. It's the product here, 6, minus the product, yeah, you're absolutely right, 4. 6 minus 4 is 2. Okay? All we're, well, no. I want to say all we're really interested in is that it's not 0. No, we need to know what it is too. Because then the inverse of A will be, what's the first part? 1 over 4, and then the next part. Two is in upper left, 3's in lower right, and what else? 1 where -1 was, and 2 where -2 was. Okay? Now, that's a perfectly legitimate expression of A inverse. If you wanted to multiply through by the 1/4, then this would be 1/2, 1/4, 1/2, and 3/4. All positives, surprisingly, but that's what you get. Now, being the cynic that I am, I want to make sure that works. That was right. So how do you check? Do the product of A and A inverse. And since they're written there, I'll do A inverse, or at least what we hope is A inverse, would be also a 2 by 2. Now, if it's not 1, you could have a mess on your hand, but we think it is. So let's do it. All right. 3/2 minus 1/2 is 1. Is that what you said? Yeah. 2/2, which is 1. Okay. So that's a 1. All right. Let's do the next one. 3 times 1/4 is 3/4 minus 3/4 is 0. Oh, that's nice. Next. -1 plus 1, 0. Next. -1/2 plus 6, well, let's see, plus, is that right? -1/2 plus 3/2 is 1. Because, see, 2 times 3/4, the 2 will go into 4 twice, so it would be 3/2. So -1/2 plus 3/2 is 2/2, which is 1. Sure enough, that worked. Okay? So that one did well. Let's try the B. Okay? B is 3 minus 1, -6, 2. What's the first thing we do to find the inverse? Determinant. So the determinant of B is what? 6 minus 6, which is 0, and that tells you not invertible. It does not have an inverse. It's a singular matrix. Now, could you have told that any other way? Well, you could do that, but here's even easier. Okay? I don't know if you remember this, but anytime one row is a multiple of another row, not invertible. And remember, if you multiply this by -2, that gives you -6, that gives you a +2. So yes. Now, not just that, this is going to come up later. You can do the same thing here. Multiply this by -3, that becomes a 3, that by -3 becomes -6. So yeah, even the rows are. So we haven't had that yet. I'm sorry, even the columns. We haven't had that yet, but the rows for sure. If they're multiple, two rows are multiple of each other, not invertible, not singular. I mean, they are. It is a singular matrix. All right, but the easy way, do the determinant, and that's what you did. Unless you just glance at it and say, "Oh, wait, those are multiples of each other. That's not going to work," and it doesn't. All right, I think we can do the properties of inverses here. Theorem 2.8. So what we have is A is invertible. Now what does A being invertible mean? Tell me some characteristic of A you know's got to be true. It's what? Not necessarily. Square. 3 by 3, 17 by 17. It doesn't matter as long as it's square. Please don't do it 17 by 17. Okay, so if it's invertible, it's got to be square. Okay? Now, K is a positive integer. Okay? C is a non-zero scalar. All right, now wait. Why use two different constants here? Wait. K has to be positive only. C could be negative. K can't be 0, neither can C. K has to be an integer. C can be any number in the world except 0. It could be a fraction, a decimal, rational, irrational, doesn't matter. K has to be an integer. Positive integer. C could be positive or negative in any number. Okay? Then, if you have those, then you can say that, what does that stand for? A inverse is also invertible. A to the K, meaning multiply A by itself K times, that's going to be invertible. C times A, that's going to be a new matrix, just with all the elements. That's going to be invertible. And A sub T, what does that stand for? Transpose. That's going to be invertible. All these are invertible. Okay? And the following is true. Okay? First, hopefully this makes perfect sense. If you take the inverse of A, then the inverse of it, you're going to get what? A. Okay, no way around it. The inverse of an inverse is the original matrix. Okay? Excuse me. Number 2. If you do A to the K and do the inverse of it, now basically what that gives you is A inverse times A inverse times A inverse. I have to write a bunch of them out there. They stop after a while. Now this is not a time plus sign, that's a time sign. Dot, 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 okay, times A inverse. and this is k factors. I guess it's all right to call them that, of A inverse. This becomes A inverse to the k. So, they didn't tell you how they did that. They just said it's true. That this is A inverse times A inverse times A inverse times A inverse, which is A inverse to the k power, like there are k factors. So basically, you exchange these superscripts. Even though this is raising to a power that's not raising to a power, this is inverse, but still you can reverse this, and it still comes out the same. Okay. Sorry. My eyes are real stingy today. 3. If you have C, A, and then take the inverse of that, okay, this may be a little surprising, but it's true. That's 1 over C, or you can think of that as C to the minus 1, but when you say C to the minus 1, you're not meaning inverse, you mean 1 over C. C to the minus 1 times A inverse. I don't know if you're expecting that, but it does work. Now, 4. If you start with the okay, I'm having trouble. Okay, what did I just do? I think I erased everything. I did not mean to. I meant to just hit the erase key. Sorry about that. Here's number 4. A transpose, do the inverse of that, and just like we did when we were squaring, cubing, whatever it was, A, same thing holds here. This gives you A inverse transpose. Okay? So the transpose, the inverse of a transpose is the transpose of the inverse. All right. If you're really into proofs, the key to proving properties 1, 3, and 4 is the fact that the inverse of a matrix is unique, and they walk you through how to do those. Okay? So it's not a bad thing to look at. Sorry, I've got my head is sort of messing up on me. Let's see, what we got? About 15 minutes more. Is that right? Yeah. I'm having trouble breathing, but I think I can make it without stopping. I hope so anyway. So I would say take a look at that. The proofs are pretty good and straightforward, and it is instructive to pay attention and see how they're doing things. All right, now, part of one of those statements up above, no, it wasn't quite, okay? Up above, when number 2 above, we took A to the k power and did the inverse of it, and we said that's the same thing as A inverse raised to the kth power. Okay? Now, for non-singular matrices, the exponential notation used for repeated multiplication of square matrices can be extended to include exponents that are negative integers. Okay? and all right. So this is for invertible matrices, meaning non-singular matrices. What we mean by a to the minus k, okay, is a to the minus 1 times a to the minus 1 times a to the minus 1 then divide that by no, don't divide, sorry. I meant to say dot, 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 a to the minus 1. Okay, let's get it the way it is. Not divide that by, but you have here k factors. Very similar to what we did up above in number 2, but the thing is these are inverse matrices here. But this right-hand side looks just like the right-hand side of number 2, and indeed it is. These are k factors, and this is the same as a to the minus the inverse of a raised to the kth power. Okay, and I think we've already said is the inverse. Well, that is indeed inverse of a to the k power. What we knew above, this was also a to the k to the minus 1 power, the inverse of a to the k. So there's lots of ways to say that, and that's another one. Now, using that convention, you can show that the properties that you would expect, it seems like we did this back when we first introduced this, but we're doing it again. A to the j times a to the k would be aj I'm sorry, I put the j as a subscript. Okay. A to the j plus k. Just like we would for real numbers. If you have a real number, well, just use 10. 10 to the third times 10 to the fifth is 10 to the 8th. You keep the base, add the exponents. You do the same thing here, even though the base is not a number, it's actually a matrix. But still that principle holds. Okay? And another one is a to the jth, and that thing is raised to the kth. Here, keep the base, add exponents. Here, keep the base, multiply exponents. The j times k. Okay? And these are true for any integers j and k. Oh, I remember now. Yeah. This looks so familiar. Before, when we were doing this, we had j and k be positive integers only. Now it's any integers. So if j or k or both are negative, still works. Okay? If one's negative, the other positive, whichever bigger, go in here. One negative, the other positive here, that would be negative because it's a product. Okay. We didn't allow negatives before. I was saying, why are we redoing this? Okay. Now, there is a little discovery here. Let's do it. Most of the time these are ahead of really where we need to be, but I think this is, I hope you'll find this very simple. A is the matrix. Goodness, my head hurts. 1, 2, 1, 3. And B is the matrix. 2, negative 1, 1, negative 1. All right. First thing it says do is calculate AB, the inverse of AB. Okay? So let's first do the product of AB. Can you do it? What size will it be? 2 by 2. So the product of AB. Let's do it. Wait. I don't know what's going on. Head's clogging up, coughing. I'm glad it's Thursday. Okay. I'm not sure I could take much more of this. About a whole afternoon of class. But we'll get there when we get there. All right. Let's multiply those two together. What do you get? 2 plus 2. Wait, 2 plus 2 is 4. Got it? Next. Negative 3, is that what you said? I can't hear. Okay, good. Okay, next. 5. And next. Negative 4. All right. Now, we need to do the inverse of that. Do you remember the shortcut, easy way to do that? Second? Okay. Find the determinant first, so let's do that. The determinant of AB will be what? Negative 16 plus 15, that would be minus 1. Okay? So what do we do with that? Well, number one, we know it's invertible. Okay? And what do we do with it? One over negative 1, which is still negative 1. So we're just going to negate this, what's on the inside. And what is on the inside? Negative 4. 4 will be your main diagonal. And 3 and negative 5 will be your cross diagonal. And then you can take the minus sign and distribute it inside. That would give you a 4, negative 3, 5, negative 4. Wait a minute. That is the same as AB. Okay? Yay or nay? It is the same as AB. All right? Now let's do A inverse, B inverse. Can you tell me just how to write down A inverse? Or at least, what do we do first? Determinant is 3 minus 2 is 1. Okay, I have a stray mark on here that, oh, goodness gracious. I'm having trouble breathing. All right. All right. All right, let's just do it. You said that was 1. Okay. 3 minus 2 is 1. So we don't have to do anything with 1 over 1. So we can just write down the rest of it. And what's the rest of it? 3 and 1 are your main diagonal. Minus 2 and 1, minus 1 are your off diagonals. Do you agree? Okay, let's do B inverse. Where do we begin here? minus 2 plus 1 would be minus 1. So this is just going to be a minus here. And negative 1, 2 will be your main diagonal. Yeah, 1 down here and no, okay. I didn't know which way you were starting. Okay, I figured it out. Okay. All right, but because of the negative sign out front, we're going to make this okay. So, I think we got that one done. Now we need to multiply those two together. A inverse, B inverse. Okay. So, I'm running out of room. 3, negative 2, negative 1, 1 times B inverse is 1, negative 1. That's a 1. It looks like a 7. One, negative 2. And when you multiply those two together, you get a 2 by 2. And what is the value? Say again? Okay. Yeah. Well, 3 minus 2 would be a 1, wouldn't it? Did I write it right? Okay. The next one over, I'm not certain of anything I'm doing now. My head is hurting so badly, but let's go for it. The 1, 2 entry would be second. I can't hear. 1, yeah, okay, good. The 2, 1 entry would be, I'm the wrong one. Negative 1 plus 1 is 0, and 2, 2 entry would be negative 1. All right. Now, yay, okay. Don't see much of interest there, but there it is, okay. But now let's do the reverse of that. Do B inverse, A inverse. And if it's all right, I'm going to come up here and do it up here. So I can keep everything on one page if possible. So B inverse is 1, negative 1, 1, negative 2 times A inverse, which we found to be 3, negative 2, helps the copyright, negative 1, 1. So let's multiply those two together, and you get a 2 by 2. And what do you get? 4. Negative 3. 5. Okay, I sort of got lost there. Minus 2, minus 4, is that what you said? Okay, I couldn't hear. And looky here, that is the same as this. So AB inverse is B inverse A inverse. Okay, now Seems like to me we had something like this before, but I think that was with transposes, wasn't it? Didn't they come out the same kind of rule? Well, with inverses, they still come out with that same rule. A inverse, B inverse, nowhere close to any of it, but B inverse, A inverse is the same as AB inverse. So, now, it says make a conjecture. I think we just did. All right, now the question is, do we have time to do example 6? What's that? How much? 3 minutes. I kind of doubt it, don't you? So let's stop there with example 6 so I can give you some homework on exercises. I knew you wanted those. Any of the odds, sorry, 1 through 5, they're all at Calc Chat. Any of the odds 7 through 29, a whole bunch of them are at Calc Chat. Now they suggest that you use some graphing utility on 27 and 29 because they are fairly big, but you can probably get by without them. Then any of the odds 31 to 35, those are finding an inverse of 2 by 2. And we didn't do the one like 37 yet, so hang off of that for a bit. We'll do that after we do example 6. Okay. And next time we should finish 2.3 and move into 2.4. 2.4 is elementary matrices. And let's see, where did we start today? Yeah, we were in 2.3, so we're in 2.3 all day today. Okay. So I'll go and shut this down.